Okay, so this is the final week of our class. I can't believe we're here already. Um, I pre-recorded it because I know you guys are busy on a Monday morning, and I figure you're going to watch it at your leisure anyway, so not a problem here. The final week deals with, and let's call it up. I want to call it up here. Bear with me. I'm going to go to our class, financial modeling. I mean, 6 weeks really flew by. It's just amazing. And once again, as always, you can find. Hold on. You could find the links to the recordings right here. So, and that was, we started on 10.5, we had a 10.19, 10.26, 11.2, and now 11.9. So it's 1, 2, 3, 4, 5, 6 meetings. Wow. Quick. Time goes by quickly. All right. So we're going to go into week 6. And this kind of wraps it up for us. This is a great class. I tell you, I really enjoyed teaching it. You can go to my Statistics Academy. I'll call it up for a minute. If you go there, because we're going to be talking a little bit about regression. You'll have a lot of stuff on calculating beta, and that's a way you can actually run a regression using Yahoo Finance. And we learned about beta, which is the relationship between the stock's price and the overall market price, and how much of the market explains the stock's price. And if you want to do it at home, you just go through these part 1, part 2, part 3, and there's actually an introduction to Yahoo Finance, and you can actually figure out how to do beta. So, and you could do it at home on your own. It's really fascinating. And make sure you take some time and do it. I mean, it's really good stuff. So that's why I put it there, and I hope you make use of it. Okay? So that's where you would find it. You'd find it right there, and I'm going to go back for a minute. And it's in this week's work right under the lesson content. But just to go into what we're talking about, let's look at the interactive learning tool. Okay. And here we go. So these are models for analysis. And when we look at a stock's price, we look at it through time series analysis, right? And time series analysis is basically used, it could be used for company earnings, it could be used in a number of ways. But when you look at a stock, time series is particularly useful because on the x-axis, and remember that the x-axis looks something like this. I'm sorry, something like this. It's the horizontal axis. I don't know why I'm not getting. Let's see if I can find this for a minute. Okay, good. So the x-axis, right, is this horizontal axis, and the y-axis is the vertical axis. And on the and I have this little background, so I hope it's not confusing. On the x-axis, we would have dates, and on the y-axis, we would have stock price. So as dates move forward, stocks would gyrate, and there'd be different prices, and they would be random prices. And they would generally trend upward because that's what stocks do, right? They generally trend upward. So, interesting stuff. But that's really one of the main things that when you're dealing with stock prices, you want to do with that type of system. Okay. So I don't know if there's any questions on that. I want to learn how to close this. Okay, good. Good. I closed it. All right. So that's how it works, right? And that's why bear with me. Got this little be a little when I share a screen, you get this small little here we go. Okay. So that's time series, and we can also do it with retailers. So you can watch a retailer's stock or a retailer's earnings as it moves across time series. And if we did it with a retailer, I'm asking for trouble, but I'm gonna do this again. If you did a retailer, you'd have this kind of relationship. Let me get a darker color. And a retailer, this would be, say, January, February, March, April. It's be yearly, and you probably would see something along the lines of, that's not good. Bear with me for a minute. You would see something along the lines of a steady movement, and then when you come to the end of the year, you would have an upward movement. And that's how a retailer's earnings would look, and then it would probably come down again when after January, and then you'd have this kind of sideways movement and then up again, and then in the fall, and then you have year-end sales that would look like that, depending on the retailer, obviously. It all depends on the retailer. So erase this, and that's just a kind of an idea as to how time series analysis works. So what we get are moving averages, and if you download the spreadsheet, you're going to get this quarterly income data, and you're going to be able to plot it. But what a moving average does is it takes away the noise in the information, right? It takes away the noise. So let me see if I can find something for you guys. You could do this on Excel, and you could do it on your spreadsheet. So let's take a look at an example of moving averages. And what happens is you have all of these random prices, right? This is a great example. You have all of these actual random prices, and this is called like a bell and candle chart, where you have each day's movement, the up and the down, and if it's up, it's green, and if it's down, it's red. But it gives you not just an idea of the randomness and the way the stock is moving, it also shows you the volatility for that day, because the larger the line, obviously, if you have stock price here, the more volatility. But if I average these things like every 50 days, usually like a 50-day average, what I'm going to get is a smoother line. So I take 50 days worth of data and I turn it into an average. And then on the next day, I take the 50 days, the next 50 days, like in other words, I'll take days 1 to 50 here. And then in my next day, I'll take days 2 to 51, and then 3 to 52. So what I'm really doing by using a moving average is I'm blending the average and I'm softening all the noise. So I'm finding a trend where here it might be difficult to detect a trend. We should get all of this volatility day in and day out. A moving average takes away some of that noise, and I get a better view of how the stock is acting. So that's the benefit of using a moving average. I would urge you to download the spreadsheet and take a look at and kind of do a moving average, which will allow you to make that smooth line. So this would be a 4-period moving average. And again, if you were actually going to look at Amazon stock, you would probably, and I know what you would see a lot of this. I'm just kind of making that up, but when I average it out, I get this very steady trend. That's one thing we observe. But I also get this smooth and upward drifting moving average. So I can actually see how this stock move without getting all the noise. And we get that all the time. We're going to always get these volatile periods in life, in any kind of nature. Think about the weather. If you look at weather in any particular day, you might get a weird day. You might get a very hot day, a very cold day. But when you start averaging them out over 50 days, you get a much smoother trend. And that's the benefit of getting this moving average. This is a 4-period moving average, where we take data from all 4 quarters and we find the moving average by plotting the average moves. So, so you get an idea of one of the devices Wall Street uses to take a look at a stock's earnings. To add a moving average graph of quarterly revenues, we click on the graph, then right-click and add the trend line. Okay, then you add the trend line. And by adding a trend line and putting the number of periods, you're going to get this moving average. Now, I just want to check something. Yahoo Finance, I believe, will also provide you with that. Here's Yahoo Finance. And let's look at, I don't know, let's pick a popular stock. I guess we could look at Apple, very popular stock. Always a popular name. I believe you can see a trend line here. And let's go to price. Charts. So notice you got this chart of Apple versus the S&P 500. Apple's done much better. And you could do a candle graph and look at it that way. But if I do a 1 month moving average, if I kind of blend it out, notice how much smoother. That's a 1 week moving average. Let's do a 1 year moving average. Notice you start to smooth out the risk. That's pretty dramatic. Let's do 1 month. It might slow down because I have another program running, so you got to forgive me on this one. But you're going to get a much smoother. Let's see if we can reload this thing. Yeah, it kind of works. It's definitely going to be slow with me running WebEx in the background. But and you can play with this yourself in any stock that you're interested in. That's a 12-month moving average. And let's take a look. All right, so this is pretty slow, so I'm going to stop here. But if you notice, you got a kind of a trend that's much smoother than what you would see if you just plotted it by the day. And here's the daily. Is this the daily? Let's take a look. It's kind of, yeah, it's hard to do it, but I tried. But at any rate, that's what you're going to get. So moving on, the next thing we'd want to look at is regression analysis. And Excel's an excellent tool for data analysis. And as I showed you in the past, you can download the data pack and you're going to get a regression analysis. And what we're really trying to do with regression analysis is we're comparing the relationship between two or more variables. And if we do that, we line up the X variables, we line up the Y variables, and we plot them against each other. And when we do that, we're going to get a, hold on a minute. We're going to get our X and Y axis. And let's say our Y axis is Apple. We'll just put an A. And our X axis, and if you watch my videos, you'll see this, is the S&P. A little sloppy. And then every time Apple moves, I'm going to plot it against the S&P. So I'm going to get this kind of trend line. I don't know why I lost that. A little bit of a tough time today, folks. I'm going to get this trend line. I see that. Oh, I'm going to have to do it again like this. Very frustrating. I'm going to get it. Hold on a minute. I'm going to get this trend line that and I'm going to be plotting my two variables. So let's see if I plot. That's what the trend line is going to look like. It's going to look like this as I move along. I'd have like Apple, and I'd have say the S&P, and I'm going to have these different points. Like say when weight is 60, height is 1.5. When weight is 70, height is 1.6. It kind of relates weight to height, and I'm going to plot these on a graph. It's going to give me my relationship of weight to height. But then I'm going to draw the best fit line in between. And the best fit line is going to give me the smallest amount of distance between the plot, the data points. The bigger the difference of the data points, the more issues I'm going to have. Right? In this particular trend, the higher the higher the height, the more weight. It's obviously a direct relationship. We see that by this best fit line. But notice as we get into higher heights, weight varies a lot more. But at smaller heights, weight is much tighter. And that would make some sort of intuitive sense. And this R squared number is the difference between these two. And it kind of tells us, to make it simple, how much this relationship explains, how much height explains weight. In this case, 49%, according to this data that we have, is how much height explains weight. That is obviously another 51% that isn't explained, and that's our job to go figure it out. But by using this plot, we can actually create this least best fit equation, which is the weight in kilograms equals 114.3 plus 106.5 times height. And what that would mean is 114.3 would be if there was zero, that's where you'd start, minus 114.3. But then every time height goes up, weight would go up by 106.5. Let's see in a stock. This is Coca-Cola versus the S&P 500. Notice this is a 4-quadrant graph because we will get returns. Now with stocks, we plot returns. We don't plot stock prices because returns give us a much better way. It's a log normal way of comparing actual rates of return. If we just plot stock prices, it's going to, if the S&P is going to have a different value than the stocks we're looking at, with S&P might have a value of, where is it now, 2,400, and your stock might have a much smaller value, like 80 or 90, and that's going to kind of skew the graph first. And the second thing is it's much more elegant to do log normal returns because now we can graph the returns on both. So here, notice that this is no return, and as returns are positive for the Coca-Cola, excess returns are returns over the risk-free rate, as we learned in the past. But as S&P returns are higher, and that's the y-axis, we can expect Coca-Cola's excess returns to also be higher, and we can expect it to be a direct relationship. Notice when the S&P starts getting negative, Coca-Cola's returns will also be negative because these points are on the same plot. You actually have a couple of outliers here. This must have been a day where maybe Coca-Cola really took a hit, maybe based on earnings, but the S&P didn't take as dramatic a hit, right? But basically, if you stay toward the middle, you see that this is a pretty tight graph. And our line of the equation is y is explained, and y is the S&P excess returns, equals 0.4893, and that's the zero coordinate, plus 0.0079 for the Coca-Cola's returns. That's actually the beta right there. That's how much Coke is going to move with the market, 0.009. So it gives you an idea of how we can calculate using time series analysis. We're going to plot, in this case, the price of Coke versus the price of the returns on Coke versus the returns on the S&P 500. And that gives you a really good example of regression analysis. Okay. So here, they actually did a weight, height, and BMI. And we're going to use the correlation function to see the relationship between weight, height, and the BMI. Correlation coefficient is 0.8785. So a correlation means there's a strong positive relationship between weight and BMI. But actually, we do have a very strong relationship. 87% between weight and the body mass index, which intuitively should make sense because body mass index should be a function of weight. Now we look at the relationship with two variables. And you can do that. You can do multivariate analysis. Now, I know some professors or some statistical experts don't like to use more than two variables. They feel it confuses the issue. Why is that? Well, one of the reasons is if I have two variables, I don't know which one is explaining the third variable. So let's say I wanted to look at exercise and calories versus weight loss or weight gain. Well, if I might see that both explain together, they explain weight loss and weight gain, lack of exercise or lack of smaller calories. They're both positive relationships, right? I exercise more, then no, you got one positive, one negative. If I exercise more and I eat less calories, my weight should go down. If I exercise less and eat more calories, my weight should go up. So that should be the relationship between the three variables. But I'm not sure if it's weight, if it's calories or exercise that's actually doing the explaining. I may get a very high positive correlation between weight and exercise versus weight loss and gain, but I'm not sure which one. It's almost like two people pushing, you're observing two people pushing a big boulder up a hill. So you know by observing it, the force that these two people are exerting on this boulder relates to how far they can get it up the hill. And there's definitely a correlation between the two people pushing the boulder and the boulder going up the hill. But what I don't know is which one of those people is doing most of the pushing. I might see two people pushing and assume two people are pushing, but it might in fact be one person doing 70% of the pushing. So it's the same thing with multivariate analysis. You may get a false read, so be aware of that. So we're looking now at LDL cholesterol levels in terms of weight and blood pressure. And we're going to just run this, and you'll run it in the Excel spreadsheet, select the X and Y values, and Excel does a great job with this. Always set the constant to 0, by the way. You know, if you set the not always, you can set the constant to 0. If you do that, you're kind of dragging the regression analysis back to 0. Personally, in my experiences, don't do that. Don't do that because you kind of skew the numbers. Now, the confidence level is a good idea because statistically, we like to have the line of reasoning is usually if you can explain, because everything has errors. Every data analysis can have errors. If I can explain two variables or three variables explain one variable, if I can do it within a 95% confidence interval, what I'm really saying is I will be wrong 5% of the time. So, and if I do 99%, I will be wrong 1% of the time. But I have no problem setting a confidence level. For mathematical reasons, I would not set the constant to 0. So 99% confidence interval is most certain, but in academia and in most studies, 95% is the acceptable standard. That still means you're going to be wrong 1 in 20. I mean, imagine if a criminal prosecutor who were prosecuting murders accepted a 95% confidence level. That would be a problem. You got to use common sense because they can't do that. In that case, 5% or 1 out of 20 defendants would go to jail for life and they weren't guilty. It'd be 5% error. So they've got to do error confidence levels like 99.9%, beyond the shadow of a doubt, because a mistake there would be putting someone away for life when they didn't commit a murder. That was a horrible, horrible mistake. So that's why the court system is really based on, especially when you have a murder trial, that you have to be beyond the shadow of a doubt, which is like 99.8, 99.9. Your stats better, and when I say your stats, they better really line up. I like to tell a class when I talk about it is, and the way you want to think about it is, let's say, and I'm a prosecutor, right? And I'm at a party for school, and we're in the middle of the quad, this big area where everybody's having a party. And, and unfortunately there's a murder. And we find out that the person who committed it, we have people on the scene, they identify, we don't know who it is, but the person who did it had a school logo on. So the detectives come back to me and says, the person who did it, everyone is identified, had a school logo on. Well, the odds of people wearing a shirt or a piece of clothing with a school logo when you have 1,000 students or 2,000 students having a party are very high. So it's not unique enough for me to want to go forward with an indictment, because I would say, well, but how many people have school logos on that night? Well, maybe 40 or 50% of the people. I'm just going to close this. And that's going to be a problem for me because I might be using that, and it's really doesn't give me enough of conclusive evidence to stop. I might unfortunately give somebody a life sentence or try somebody for murder that shouldn't have been tried. So I send the detectives out again. And the next time they come around, they said, well, we found a sneaker print that's related to the person, the suspect. And then we run the numbers, and only 1/10 of 1% of the population would even have a sneaker like this. and maybe 1 out of 10,000 people have sneakers like that. Let's use that. Well, now that is unique enough for me to want to go further because now I have a very high confidence level. So that's how you want to think about confidence levels. It's your margin of error. And depends on what you're doing. If you're doing a very simple analysis, like a stock analysis, and you're just trying to determine the trend on the stock where there's so many variables, and you're not like, it's not life and death, you can live with a 5% confidence level. But if you're a prosecutor prosecuting major crimes, then you better have a very high confidence level. Or if you're testing a vaccine, right? Now we know the whole COVID story. If you're testing a vaccine, well, you definitely want to have a very high confidence level. And then we just do our output and select OK. And this is going to be what an output looks like. So this is a classic output. And what this tells us is we're only explaining 1.3% of the time. Whatever we're measuring here, it only explains 1.3%. So it's really not a good fit. It really is not a good fit because we have very little explanation. Now, if I go down here by the regression analysis, I had 299 data points. That's the sum of the squares. That's my F statistic, and that's my significance. So it is 0.048, which is close, right? So it does tell me that the 2% I've explained is I can have some confidence in it. But on the other hand, I'm only explaining very little. So it's good and bad news. What little I explained, I could be confident in, but I've got possibly, because that's what an R squared is. It tells me how much my data points explain my relationship. That means 98% of the time, 98% of these data points only explain 2% of the relationship. So if I was comparing, say for instance, like one stock versus the S&P might only explain 2% of the movements in the stock. Maybe it's a stock that has no relationship to the S&P. So now I've got to go out and figure out what the other 98% is. But at least I know the 2% I did explain has a higher confidence. And the intercept right here is right here. It's where the zero coordinate would be. So if I set one variable to 0, if the x coordinate is at 0, the y coordinate's at 72. And every time I move weight up, the is a positive relationship. It should go up 0.257 in weight. How do we determine how well the multiple regression equation fits? The R squared. And as I said, this example, only 2% of the variance in LDL levels can be explained by the systolic pressures and weights. The problem with R squared is that as more variables are included, the calculated R squared value increases even when R squared value can remain the same. So what they're really saying to you is if I add more stuff in, I'm going to get more explanation, but it's kind of going to be spurious explanation. Spurious meaning I'm really not sure if it's right. It's just that I'm adding more variables and it's going to count for more information, but I'm not going to be sure what I'm explaining. You know, adding a lot of variables to a multiple regression can be really tricky. I had one student years ago who did a project for me. She was the golf coach. And she took on and she had the players fill out these data sheets on every hole they played. And in the end, she had a lot of different things. How many times you went in the sand, how many times you were in the fairway. And she ran a multiple variate analysis, but she had a break there because she found that when she added confidence, it explained a lot of that golf score. And intuitively, and you always want to use intuition, intuitively, golf confidence has a lot to do with sports, and it certainly has a lot to do when you're playing golf. You know, the more confident you are, the more certain you are, the more certain you're going to strike the ball. You're going to be more confident on your puts. You're going to get putts. You're going to get a better score. So more variables doesn't necessarily be a good thing. But here, because it's a low number, it's not a good fit. Although the p-value is not low, so we could be doubtful, but I got to kind of agree and disagree. What little we have explained is a good fit. So we looked at 3 components. And the methods we covered tell you a great deal about a data for most circumstances. But if you require more rigorous analysis, you have to do more complete and thorough regression analysis, meaning your data must be better. You have to do more work. You have to maybe look for test different variables. And eventually you're going to get a better test of your regression analysis. So there's a lot of problems that can come about. One of the problems we see sometimes is, so this was a typical plot. There's some typical problems we look for right away. in regression analysis. I'll go over a few of them. There are outliers. What's that? I can have a linear regression outlier. And what does that look like? This is one of the issues I'll have. I can plot two things against each other, two variables against each other. In this case, I don't know what this is, but it's, well, let's see if I can find it. Here's one. This is, one set of data versus another. Notice a lot of the data is very kind of clean and linear. When I move this up, I have a direct relationship. And that kind of makes sense to me. But there's always going to be, but up here, I've got this outlier. Maybe I have like a classroom of children, and I notice that I got heights and weights. And this is like, let's say sixth grade class, and I got somebody who's 4 foot or 5 foot, and their weights are a little higher. And this is what I would expect. And then there may be one kid in the class who's like 6 foot tall, like seventh grade. Just happened to be somebody who grew a lot. That's an outlier. And what it does is it drags up my whole average. But if I take away the outlier, I get a very good fit. The outlier might throw my numbers out a little bit. So that's one issue. Here's another one. Do I drop it or not drop this thing? That's a question. You don't just drop the outlier without thinking about it. If the outlier can truly exist, you leave the outlier in. But if it's not a possibility, then it could just be, first the question you might ask is it a bad data point? Right? Is it a bad data point? This might be money people spend on food and their incomes. And so I've got, kind of looks like, as people make X amount of dollars, they're spending various amounts on their food budget. And that's kind of not really tight, but tight enough to show me that there's this relationship here. And then I might have one family that has a lot of income and spends a lot more money on food. Now, do I take that outlier out? Maybe not. If that happens from time to time, it's a decision I've got to make with the people I look at my data with. Right? Here's another one. I've got a lot of data that's very close. And then I have this outlier, number of pubs and deaths on the roads. And this is probably very indicative. And this might be, one that's an outlier. So do I take it out? Question is, how do I feel about the outlier? So that's one thing you want to look for in a regression analysis. Another one is heteroscedasticity. That's a weird word. Heteroscedasticity is a problem we also get with regression analysis, where on lower levels or at one level of the regression, we have numbers that are very tight. But as the numbers grow, the regression becomes more dispersed. So that's another thing that we visually look for. Why do we look for all these things? Because they're common, and there are tests. As you get more sophisticated in doing regression analysis, you'll start to know how to detect heteroscedasticity, and you'd run tests against it. So what could this be? This could be a problem where, when I have incomes versus, again, food budget, at lower levels of income, everybody kind of spends the same amount of money for food because people have basic needs. But as people start making more and more money, the relationship between food budget and family income becomes more dispersed, because some families will just eat the same or eat a little less, or they spent enough. This is enough food for anybody, no matter how much money they have. And then maybe some people start buying rare wines, expensive stuff. So you get this bigger dispersion. That's just one example. But when I see this dispersion grow more and more as the data grows, I know I have this heteroscedasticity problem. So that's another one. One other one we might get is something called spurious. Here's another bad. Here's a really weird one. So, whenever I see these patterns, so whenever I do a regression analysis, I always want to run the plots against it, because just visually I can get an idea. Another one is something called spurious correlation. If I test enough data, I might get a relationship that isn't true, but looks true on a regression. I remember once somebody did a regression of snowfall in Amherst, Massachusetts versus the unemployment rate. And they found a very specific relationship between snowfall in Amherst, Massachusetts during the winter months and the inflation rate. And there was a real correlation. Now we know that there's no reason that snowfall in Amherst should explain the inflation rate. However, it did, because we just happened to stumble upon two variables that relate to one another for spurious reasons, or for reasons that, that are just lucky, just by chance. So that's another correlation that we have to be very careful of. So these are just 2, 3 of the more common examples. And we got multicollinearity, which we talked about, of the more common examples of problems you could find when you do regressions. Okay, here's one. Here, look at this one. Films Nicolas Cage appeared in, and swimming pool drownings. Horrible stuff. But there's a correlation. Now we know the films Nicolas Cage appeared in has nothing to do with that, but it's just a spurious correlation. The marriage rate in Kentucky and fishing boat deaths. They're related. No relation, but it's spurious correlation. Okay. Per capita consumption of cheese, number of people who died, but why do I have these horrible things? Died getting caught up in there. So it's just spurious correlation. It's just correlation that happens because we looked at so many numbers, we finally found a relationship. What does it mean? It's the connection between two variables that explain or appear causal, which is the word we use, but they're just not. All right, so that'll wrap it up. Make sure you finish all of your work. The key code word is clock. The code word is clock. The code word is clock. So make sure you do finish your work. All right, really important that you do that. And, put everything in. I'll be grading. I'm very happy with the work you're doing. Keep up the good work. And you know where to reach me. You know my text, 917-613-9725. If you have any issues, 917-613-9725. Let me know if you have anything and you need anything. It's great dealing with you guys. You're very nice and very terrific. Talk to you later.